Hi there. Thanks for stopping by. Just caught me counting some of my money here. Money is obviously a pretty important thing, which brings us to probably my favorite part of our course. Now that we've finished exponential functions and exponent laws, we move on to a unit on personal finance. Finance is anything to do with money. So we get to learn some new math skills that will allow us to solve problems about saving money, investing money, borrowing money, maybe to buy a car or a house or to go to school, those kind of things. And as we're working through those concepts, I will throw in as much practical advice about personal finance as I can. So we're going to start with savings and interest. Let's get started. So let's start by talking about interest. One question you might have is, what is interest? Well, interest is the cost of borrowing money. It also could be looked at as the reward for saving money. It's almost always expressed as a percentage, and a percentage per year. So how much money you would make as a percentage per year if you saved your money, or how much it would cost you to borrow money per year if you were borrowing money. So to start with, when we look at interest calculations, we really need to start with something called simple interest. Simple interest is a quick way to calculate interest, and it's basically how you would calculate interest if you didn't know anything else about interest. It's done using the formula I equals P times R times T, where I is the interest earned in dollars. P is what's called the principal, which is the amount invested or the starting amount of the investment, the starting amount of the savings. R in this case is the yearly or annual interest rate, and that's as a decimal, okay? So if it was 5% interest, it would be 0.05. And then finally, T is time, and since our interest rate is per annum or per year, then time must also be equal to years as well. Let's look at an example. Sheldon puts $3,000 into a GIC that collects 4.5% simple interest. Let's just unwrap in this question a little bit. What's going on? Well, a GIC stands for a Guaranteed Investment Certificate. That is something that you could, savings option that you could buy at the bank. And the only thing Guaranteed Investment Certificate means is that your interest rate is guaranteed and you're guaranteed not to lose any money either. So you're going to get your money plus your interest, and that's a guarantee they offer. Usually the trade-off between a Guaranteed Investment Certificate and just a regular savings account, the GIC will usually offer a higher interest rate, with the trade-off being you actually can't access your money. So, for example, if Sheldon bought this GIC, it might be a 4-year GIC, in which case, he can't touch his money for 4 years. So using our simple interest formula, I equals PRT, we can calculate the interest you'll earn in 4 years. The principal is the $3,000. The interest rate is 4.5% as a decimal, divide by 100. That's what you get. And the T, time, is in years, 4 years. Now notice the little /A here. That stands for per annum, and an annum is a year, so that just means 4.5% per year. If you type that into your calculator, you get $540. So that is the interest that you would earn in 4 years, $540. What's the total value of the GIC? Well, he still gets the $3,000 back, of course, plus the $540 is going to give you $3,540 final value of the GIC. So in this example, Sheldon gets $540 in interest. He gets that over 4 years. If you take 540 and divide by 4, you actually get 135. So he's really getting $135 every year in interest, and that doesn't change. Now, it's possible that GICs work this way, but it's not that common to have simple interest. Instead, you might ask yourself, what happens to Sheldon's interest each year? Like, what happens at $135? Does he get it? Does the bank just keep it and pay him all the interest at the end? Well, the answer to that question kind of introduces compound interest or interest on top of interest. Suppose at the end of each year, when Sheldon has earned his $135, suppose he has that money put back onto his GIC. So the next year, there's actually more money that's collecting interest because the interest has been added to the investment and now that collects interest. So you're taking a percentage of a larger number. Let's look at what happens to his money in this case, and we'll use a table to start. So at the end of year one, at the beginning of the year one, he has $3,000, and during that year, he earns 3,000 times 0.045, which is $135 in interest. If we then take that $135 and we add it to the 3,000, we could say that he has $3,135, and that is now his new principal for the beginning of year two. At the end of year two, or by the time year two is ended, we then say that he's collected interest on that $3,135. Now that actually works out to $141.08. So a little bit more. Instead of earning $135, he actually got $6.08 more in interest. You then add that to the $3,135, okay, plus the interest he's earned. And he now has $3,276.08, and that carries forward to the next year. Okay, let's just continue doing that and see what we get here. And there you see the rest of the calculations. And in this case, with his interest being added to the principal every year, Sheldon finishes with a little over $3,577. So it does make a bit of a difference. It's $37 more money at the end of the 4 years just by taking the interest earned and allowing it to earn interest. Now, is there a shorter way to solve this problem? There actually is. And if you think about our last unit, we talked about exponential growth. This is an example of exponential growth. Sheldon has $3,000, and every year it's growing by 4.5% per year. It's actually the exact same as thinking about, say, a population of a town being 3,000 people, and the town's population by growing by 4.5% per year. And hopefully you would realize that the way to do that question is to take $3,000, multiply by our growth rate of 1.045. Okay, remember we add 1 to make it a growth rate, to the power of 4. And sure enough, that gives you exactly the same thing. So it's not necessary to do this table. So in this example, Sheldon's interest started collecting interest at the end of every year. However, what about, why does he have to wait a year to get his interest? Imagine at the end of every 6 months, the interest was added to the principal and it collected interest. In fact, we really would like interest to be added or calculated as soon as possible so that it can start collecting interest as well. Every 6 months is called semi-annually, or twice a year. So imagine Sheldon's interest was compounded semi-annually instead. How would that change the problem? Well, at the end of 6 months, he's going to get some interest, but he's not going to get 4.5% in interest. He's going to get 4.5% divided by 2 because it's only been half a year. So our new growth rate is 0.45 divided by 2, which would be 2.25% or 2.25. Okay, I didn't write 2.25 here, but I could have. Now, he doesn't get interest 4 times, though. He gets interest 8 times because now we're talking about a growth rate every 6 months or twice a year, not every year. So although the interest rate goes down, he gets interest twice as often. If you plug all that into your calculator, you should get an answer, and it's going to be a little bit higher than the amount up here. and it actually is 3,584.49. So a little bit more money by getting his interest every 6 months. Now, I think the next question seems pretty obvious. What about if it's compounded every month? Why not get his interest at the end of every single month, have that added to his balance so that it can collect interest as well? This is probably what happens if you have a savings account. Likely you notice at the end of the month your interest is put in the bank account and then it starts collecting interest as well. So in this example, we still have $3,000 for our initial amount. Our interest rate is much, much smaller though, because you're getting it every month. So I take 0.045 and I divide it by 12. That turns it into a monthly interest rate. However, over 4 years with 12 months in a year, he's going to get interest 48 times. So the growth periods are 48. Now our time is kind of in months now, not in years. If you take a minute and figure all that out, and be careful here, you don't want to round 0.045 divided by 12. The reason you don't want to round that is because you're going to take it to the power of 48. So any rounding you do is really going to blow up. So it's actually best to figure out how to do all that in your calculator at once. So when you get this number 0.45 divided by 12, you want to leave that button on your calculator. Your calculator stores, I don't know, maybe 20 decimal places or something. So what do we get for this? We plug all that in. We should get $3,590.44. So a little bit more. We can see from that previous example the difference between simple and compound interest. Compound interest is an example of exponential growth. We're multiplying, in that case, by 1.045 every time, or whatever it might be. Simple interest, you get the same amount of interest every year, so that's a linear growth. Now, compound interest is so common in finance that it has its own formula, and there's the formula right there. It's basically the same as the formula we looked at for exponential growth, where we talked about the formula for exponential growth being y equals a times b to the power of x, where a is your initial amount and b is your growth rate. That's all we've done here. We've just replaced the initial amount with p, and p is the principal or starting amount of the investment. We've then taken the b value, the growth rate, and we've said it's now the interest rate plus 1, and so that's why there's a 1 plus I. And then the x is now been replaced with n, and n stands for number of compounding periods, kind of like time. And then finally, a is the final amount instead of y. Now, a couple things to be careful of. N is the number of compounding periods, the number of times your interest is calculated. So if your compounding period is monthly, that means n is the number of months. If it's semi-annually, that means it's the number of years times 2. I is the interest rate per compounding period. So if it's a 6% interest rate, but it's compounded monthly, you have to take your 6% and divide it by 12. If it's 5%, but it's compounded semi-annually, then you divide by 2. We'll see that with a few examples below. It's common compounding periods annually once a year, semi-annually twice a year. Quarterly would be every 3 months or every quarter. That's 4 times a year. Then finally, we could talk about monthly compounding every month, as well as daily compounding as well. That'd be 365 days a year or 366 days a year if it's a leap year. Now you might say, why do I have to wait even till the end of every day to have my interest calculated? Couldn't I do it every hour or every second? And the answer is yes, you could. You would find it doesn't make much of a difference. In fact, you can even compound what's called indefinitely, which is kind of like infinitely compounding. We're not going to worry about that in today's lesson. As an example, we could use the compound interest formula to solve any problem with compound interest. So here we have, I'm just going to write the formula down and sub in things. We have a $6,000 investment, so our principal is $6,000. Now our interest rate is 4% per year, but it's compounded quarterly. So you're only going to get that every, we have to take our interest rate and divide it by 4. Because you're only going to get a quarter of the interest rate if it's compounded quarterly. However, our n value is 5 years times 4 times a year is 20. So 20 times your interest is calculated. Notice that you always kind of take n and multiply it, and I and divide it. That's kind of a good way of thinking about it. Now, if you want, this one does work out nice in that 0.04 divided by 4 is 0.01, so it's the same as getting 1%. If you do that work, you should find you get, I'm just going to plug that in my calculator now. Get $7,321.14. Okay, take a look at the next one. See if you can set up the formula correctly and solve it. So there's the solution. It was a $3,000 investment, so our p-value is 3,000. Our interest rate was 3.4% per year, but compounded monthly. I had to divide that by 12 when I subbed it in for I. And then n, our number of compounding periods, or our number of months in this case, 2 years, times that by 12 to get 24. Plug it into your calculator, and there is your answer. Now, perhaps you're having trouble with this step of plugging it into your calculator. I can show you on the calculator I have on my computer here what that would look like. So I pull my calculator up, and I'm recommending, if you're having trouble, start with the 0.034 divided by 12. So 0.034 divide by 12. Okay, so then I figured out that amount right there. I don't want to round that. I'm going to add it to 1. Okay, I get in there, I get that. And then to the power of 24, so my power button, 24 equals, and then finally take that and multiply it by 3,000. And there's your final answer of $3,210, and if it's rounded correctly, 79 cents. Do need to be able to round to the nearest cent correctly when we deal with money. Okay, look at this next question, which is a little bit vague. Find the final value of a $10,000 GIC compounded daily for 3 years, how much interest was earned. So I've given you an amount, a $10,000 GIC, and the time, 3 years, compounded every day. There's no interest rate though, and in fact, where am I coming up with these interest rates in the previous examples? Are they realistic or not? Why 4%, why 3.4%, and so on? Well, there's a few things you should know about interest rates when it comes to saving money. If you're willing to not access your money, you're probably going to get a little bit more interest. Potential for highest interest rate would be if you're willing to take some risk with your money. So have someone invest in the stock market or have someone invest in the stock market for you and try for a higher rate of return. That's what this table here tries to summarize for you. You could think of the return here as really just being the interest rate, and this being the amount of risk you're willing to take. As you're willing to take more risk, there's a potential for a higher return. So that's something to think about as well. Another thing is that interest rates change over time, quite a bit sometimes. One thing you probably heard in the news, especially recently, is something like Bank of Canada lowers prime interest rate or something like that, or the Federal Reserve in the United States. What that means is when the Bank of Canada lowers the prime interest rate, there's a chain of events that happens that causes the banks to very quickly lower their interest rates as well. Now, why would the government and the Bank of Canada want to do that? The idea is if interest rates are really low, then people are discouraged from saving their money. So they're more likely to buy things with their money or to invest in stocks and invest in the stock market. So one thing that the Bank of Canada will do to help the stock market and help the economy is lower interest rates so that people are more likely to keep their money in stocks and not save their money or sit on their money, as some people might say. It's not just people, it's large corporations with a lot of money as well. So that's partly what's going on right now and why interest rates are very low. So CIBC was the first bank I thought of, so let's just take a look. I pulled up their website with their GICs on it. So here are their GICs they offer. A 1-year GIC is 1.35%, so not very much interest. And if you want a flexible GIC, that's over here, where you can actually get at your money, then it's 1.25%. If you're willing to part with your money a little bit longer, the 3 years will give you 1.45% and 5 years, 2%. I'm sure CIBC sells investment packages with higher interest rates, but some risk associated with it. Or what you might say is an interest rate that's not guaranteed. You can only go on what's happened in the past. You don't necessarily know how much money or how much interest your money is going to make. In any case, in this example, it was 3 years, so it'd be 1.45%. So we're going to use that amount. So if you start with 1.45% compounded daily, why don't you go ahead and plug those values into this formula and see what you get, and I'll do the same thing. So there's the rest of the solution to this problem. My principal, of course, is 10,000. Okay, the interest rate of 1.45% that we looked up, we have to divide that by 365 because it's done per day. That gives you a very small number. But there are 3 years times 365 days in a year would give you 1,095 compounding periods, or 1,095 days. Now, I assume none of those 3 years was a leap year. If it was a leap year, you'd have to actually do that year separately. And so there you go. Even at a very small interest rate, notice that you do still get $444 on $10,000. That's free money, so might as well take it. Okay, there's some questions for you to try. Good luck, and I'll see you later. Actually, quickly before I go, I guess I did technically forget to answer the question. The question was how much interest was earned here. Well, we had our final amount of $10,444.59. Okay, that was more than $10,000 because of the interest. So just subtract $10,000, and that gives you the interest earned, which is $444.59. That's your interest earned. Keep in mind that the simple interest formula, I equals PRT, that formula gives you the interest that's earned, just the interest. But the compound interest formula gives you the final amount with interest. So the two formulas are a little different that way. Okay, bye for now.